Welcome to the Deep Dive. Today, we're pulling back the curtain on something most people never think about, but it's incredibly vital.
Yeah, we're talking about the nuts and bolts, the actual network configuration behind emergency systems like 911.
Exactly. We've got some study materials here, and we're going to dive into how these emergency calls actually connect, the tech involved, and, why understanding this matters for getting your call from you to the help you need.
It's like exploring the hidden infrastructure, the pathways that make 911 work when you need it most. It's not just magic.
Definitely not magic. So let's start at the beginning, right? The foundational stuff. How are these networks physically structured? The study guide talks about switching configurations and telephony.
Right, so how telephone switches are actually deployed depends a lot on the area they're serving. Is it a small rural place or a big city? That affects the configuration.
Makes sense. Scale matters.
Exactly, and scalability is always a consideration. You need a setup that can grow or adapt.
Okay, so the material mentions a couple of main types. First up, the standalone configuration. What's that about?
Think of standalone as like a self-contained unit. It's designed for a specific geographic area, usually served by one central office switch.
Like one main hub.
Pretty much. It provides service directly to that area.
Mm.
The material also notes it can serve one or more remotes, maybe smaller pockets nearby.
Okay, and that idea of remotes sort of leads into the next type, right? The host remote configuration. Sounds a bit more complex.
It is, and it leans heavily on digital switching technology. You have a central, powerful host switch. Think of it like the main brain.
Gotcha.
Then you place smaller remote units out closer to the customers. These remotes aren't fully independent. They get their instructions, interpret things, and execute functions based on communication with the host over a data link.
Okay, but here's where it gets really interesting and honestly critical for 911 systems. These remotes have a special mode, emergency standalone.
Yes, absolutely vital. This is all about resilience. If that data link between the remote unit and the host fails, maybe a fiber cut or some other big outage.
Right, if the connection breaks.
Exactly. The remote unit can automatically switch into this emergency standalone mode. Even without the host connection, it keeps the essential functions going.
So it can still process 911 calls locally, even if the main brain is offline for that remote.
Precisely. It can keep the local 911 trunks connected to the PSAP, the public safety answering point, up and running. The study guide really stresses how important this is for contingency planning, disaster recovery. It makes the system much tougher.
That's a huge safety net built in. Wow. Okay, the material also threw out a term, pair gain. What is pair gain?
Pair gain. It's basically a technique to squeeze more phone lines onto fewer physical wires.
Like getting more bang for your buck from the existing copper.
Exactly. It uses multiplexing, sort of combining signals to carry, say, 24 conversations over maybe just 2 pairs of wires. Instead of needing 24 separate pairs, you gain conversations per wire pair.
So it avoided digging up streets to lay tons of new cable back in the day.
Pretty much. It was a very efficient way to expand capacity using the infrastructure that was already there. A bit of unsung hero tech.
Okay, so that covers the basic structures. Now let's talk about the intelligence directing the calls. The guide introduces the E9-1-1 Selective Router, sometimes called a 911 tandem.
Right. This is the real brain of an enhanced 911 system. It's a specialized switch. Its whole job, its main purpose, is routing 911 calls accurately.
How does it do that?
It looks at where the call is coming from, the caller's geographic area, and uses complex routing tables to figure out the exact PSAP that's responsible for that specific location and sends the call there.
Like a super smart traffic cop just for emergency calls.
That's a good analogy, yeah. Making sure every call gets to the right destination quickly.
Now, calls usually start at the local phone switch, the end office. But the material says sometimes calls might bypass the end office's own screening or routing rules. Why would that happen?
Well, it can happen, especially in areas where different selective routers serve overlapping jurisdictions. It gets complicated. But the study guide is pretty clear on this point.
Yeah.
NA, the National Emergency Number Association, strongly advises against using those regular end office translations for routing 911 calls.
Why is that? Seems simpler, maybe.
Because those end office rules are for general phone calls, not the super precise geographic routing needed for emergencies. They're just too high a risk of errors. The selective router is built specifically for this job with the right data.
Right. You want the specialist handling the critical task. Makes sense. And this selective router does more than just routing, correct? The guide lists other features.
Oh yeah, it provides a whole toolkit for the PSAP call takers. Besides the core selective routing, there's transfer, letting the operator send the call to fire or EMS dispatch smoothly.
Mm-hmm.
Then there's call conferencing, basically three-way calling. Super useful for bringing in a supervisor or maybe a language interpreter or another agency if needed.
What about the others listed? Speed dialing, alternate routing, default routing.
Speed dialing is often like a one-button transfer to frequently needed numbers. Alternate routing is crucial if the main PSAP is swamped or, worse, down. The router automatically sends the call to a predefined backup PSAP.
A fail-safe.
Exactly. And default routing is the ultimate fallback. If the router somehow can't figure out the right PSAP, maybe the location info is missing or garbled, it sends the call to a designated default center. Ensures the call goes somewhere.
Those aren't just bells and whistles. They sound essential for handling real emergencies. But okay, here's a tricky situation the guide mentions. What if you live in an area technically served by one selective router, but your actual local PSAP connects to a different one? Inter-selective router calling.
Yeah, that's a headache. It happens when the technical network boundaries don't perfectly match up with, say, county lines or city limits that define PSAP responsibility.
So how do they fix that?
The guide mentions two ways. One is building a dedicated physical trunk group, basically, a bunch of dedicated lines directly connecting the two routers. But it notes this is usually expensive and, frankly, inefficient.
Okay, so what's the better way?
The preferred method is using inter-machine trunks, or IMTs. The guide points to these as the standard solution.
IMTs.
Yeah, inter-machine trunks. They let the different selective routers talk directly to each other, sharing the call info and routing instructions needed. It basically smooths over that boundary problem. The call gets routed correctly no matter which router picked it up first. The guide even mentions a NINA standard 03003 that defines how this works.
So IMTs act like the diplomatic channels between these routing brains. Good to know. Let's zoom back in on selective routing itself. How does the router know precisely where to send my call?
It all comes down to location information. An enhanced 911, it usually starts with your phone number, the ANI, or sometimes a pseudo ANI for certain types of calls.
Okay, it gets the number. Then what?
It uses that number to look up your information in a special database called the ALI Automatic Location Information Database. Ideally, the ALI contains your civic address validated against the MSA.
MSA.
Astor Street Address Guide. It's like the official directory of all valid street names and address ranges within a 911 service area. It's used to make sure addresses are correct and to map them to the right PSAP.
So number, lookup address, and ALI check address against MSAG. Use MS data to find the right PSAP boundary route to call.
You got it. That's the basic flow. The selective router has tables linking those MSD-defined zones to specific PSAPs. The material also mentions newer systems, like Next-Gen 911, will use even more precise data, like geographic coordinates, often in formats like PIDF low. Sometimes time of day or call type might also influence the routing slightly.
Wow, that's a lot happening behind the scenes in just seconds. Okay, we've got structure, we've got the routing brain. How do these parts actually, communicate? And how does the voice itself travel? Let's talk signaling, data, and transmission.
Right. Signaling is like the network's internal messaging system. It's the control information passed between switches and other elements to set up calls, manage them, and tear them down.
What kind of info?
Things like, hey, ring this phone, or send this call over here, or this line is busy. Even billing info in older systems, it's all control plane stuff.
The guide mentioned SS7.
Yes, signaling system number 7, or SS7.
Mm-hmm.
It's a very common type of what's called common channel signaling. Think of it as a separate dedicated data network just for these control messages.
So the control signals travel on one road and the voice conversation travels on another.
Exactly. It's much more efficient and faster than the old way.
Which was?
In-band signaling. That's where the control tones or signals actually use the same channel, the same pathway as your voice. Examples mentioned include multi-frequency or MF signaling, and even DTMF to some extent, though that's more user-to-network.
Okay, speaking of older tech, the guide brings up CAMA Centralized Automatic Message Accounting. Sounds like phone billing.
It totally originated from phone billing. Decades ago, it was developed to track long-distance calls centrally for charging purposes. It collected all the call details.
So how did a billing system end up in 911?
Well, it was already deployed in many phone switches, and critically, it had the ability to capture the calling phone number, the ANI. And that ANI became absolutely essential for E9-1-1 to know who was calling and where to route the call based on their location lookup.
So they repurposed the billing mechanism to send the caller ID for emergencies.
Clever.
It's a great example of adapting existing tech. The material notes an important evolution with CAMA, too, related to getting the full 10-digit ANI, including the area code, for all calls. Originally, CAMA didn't always handle that smoothly, especially with calls coming from different areas or mobile phones.
Right, you need the area code to know which 555-121 it is. Precisely. So the guide mentions a standard, ENP 03002, about enhanced MF signaling, which helped ensure that 10-digit ANI got sent reliably over that CAMA channel. It also notes the exact CAMA format might differ slightly depending on where the call comes from, a landline office, a wireless carrier, etc.
Okay, quick clarification then. Multi-frequency, MFMF, and dual tone, multi-frequency, DTMF. They both use tones, but what's the difference in practice here?
Good question. They both use pairs of audio frequencies. But generally think of MF as the language switches used to talk to each other over trunks in the network, fast bursts of tones for routing. DTMF is what you generate when you press the buttons on your phone, touch tone dialing. It's typically user-to-network signaling.
So MF is the network's internal chat, DTMF is you talking to the network.
That's a pretty way to put it. While both use tones, their main application in this context is different. And yeah, DTMF is the technical term. Touch tone was the Bell System brand name.
Helpful distinction. Okay, that's signaling the control messages. What about the actual voice or data transmission? The guide talks about the big shift from analog to digital.
Right. The old phone network was all analog. An analog signal varies continuously, like a smooth wave. Think AM/FM radio. That copper wire pair coming to your house traditionally carried an analog voice signal.
Still does sometimes, right?
Sometimes, yeah, in the last mile.
Yeah.
But the core network, and increasingly the connection to homes and businesses, moved to digital.
And digital is?
Digital signals are discrete. They represent information as a series of distinct values, usually ones and zeros, on or off. Think of a square wave instead of a smooth one.
Why the big move to digital? What were the advantages?
Huge advantages: capacity, speed, clarity. A key digital technique mentioned is TDM, time division multiplexing.
We mentioned multiplexing with pair gain. Similar idea.
Sort of, but applied differently.
Yeah.
With TDM, instead of needing a whole physical circuit for your one call, multiple digital calls can share a single high-capacity path. Each call gets assigned a tiny repeating time slot.
Like tiny slices of time on the same highway.
Exactly. It lets you pack way more conversations onto the same fiber or copper link. Another big plus is signal regeneration. Analog amplifiers boost the signal and any noise it picked up. Digital repeaters read the ones and zeros and create a perfect, clean copy. Much less noise degradation over distance.
Ah, clean copy every time. That's a big
Right.
difference. The guide also briefly mentions packet transmission, like VoIP.
Yeah, voice over IP or packet networks are kind of the next step built on digital. Instead of a dedicated circuit for the whole call, your voice gets chopped into little data packets.
Little envelopes of sound.
Kind of. And these packets get sent over the data network, maybe taking different routes, and then reassembled at the other end. It uses network resources really efficiently.
It's amazing how many layers there are. Structure, routing, signaling, transmission. Okay, let's try and pull this together. The study guide mentions different types of 911 systems that use these technologies.
Right. It boils down to basic 911, enhanced 911, E9-1-1, and the future, next generation 911, NG911.
Let's focus on basic 911 first, the earliest version, right? Recommended way back in 57, first system in 68. How did that work with the tech we've discussed?
Basic 911 was just that basic. It gave you the single number 911. Calls were typically routed at the local central office, the Class 5 office. It would just send all 911 calls from its area to one single pre-assigned PSAP, often using existing tandem trunking, but without the smart selective router software.
And the limitations. What problems did E9-1-1 solve?
Several big ones. Critically, basic 911 didn't automatically provide the caller's number, ANI or location, ALI, initially. The PSAP operator had to ask, "Where are you?"
Wow, okay.
Also, the routing was based on those telephone exchange boundaries, which often didn't line up with police or fire department jurisdictions, so you could easily get routed to the wrong town's dispatch.
The jurisdictional overlap problem.
Exactly. And connecting with different fan companies was pretty basic just through that simple tandem arrangement.
So E9-1-1 with the selective router, ANI, ALI, and those features like transfer and alternate routing was a massive leap forward to fix those specific issues.
Absolutely. It added the necessary intelligence and data lookup to route calls accurately based on location and provide the call taker with critical information automatically.
And NextGen 911 builds on that, moving towards IP networks.
Right. NG911 leverages the digital and packet-based networks we talked about. It's designed for an all-IP environment, handling not just voice, but text, images, video, and using much more precise location data. It's the next evolution.
This has been incredibly informative. We've gone from the physical structures like standalone and host remote and appreciated why things like emergency standalone mode are so vital,
And how pair gain helped expand networks efficiently.
to the absolute core intelligence of the E9-1-1 selective router, handling that precise routing, providing tools for the PSAP, and using things like IMTs to bridge network gaps.
We also unpacked signaling SS7, the evolution of CAMA, from billing to providing ANI, the difference between MF and DTMF, and the huge shift from analog to digital transmission, including TDM and packet networks like VoIP.
Understanding these pieces really helps you appreciate how complex yet hopefully reliable that 911 call process is. It's not just picking up a phone.
Definitely not.
Yeah.
And knowing this foundation is key to understanding how the system keeps evolving, adapting to new technologies, and how we communicate.
It really does give you a whole new perspective on just dialing those three numbers.
Yeah, it does.
So here's something to think about as we wrap up. That simple act, dialing 911, kicks off this incredibly complex sequence of events we just walked through. Switches, routers, databases, signaling protocols, transmission methods, all working together in seconds. Now think about the future. How will things like texting or sending video or sensor data to 911 change things? How will next-generation systems leverage these advancing network capabilities even further? It's a constant evolution to keep that lifeline strong and adaptable.
It really is. A system built on layers of technology, always needing to keep pace with how we live and communicate, ensuring help gets there when it matters most.